Quick refresher from last lesson. If I have a circle with a central angle of 82 degrees, what is the measure of arc AB, Travis? It is 82 degrees. Okay, so yesterday's stuff was pretty tough, right? No, not so much. Okay, it wasn't super hard. Now, obviously, there's more to it than that. There was adding some things. You had to solve some equations. That made it a little bit more difficult. But the general idea was not hard, correct? Okay. Today is going to get a little bit more confusing. We're going a little bit more in depth with this. So we're continuing 10.2. My board's been messing up all morning, so you're going to have to bear with me. Okay, the first things that we come across is new theorems. Now, there's no reason for us to try to give these a name because we're not going to use them in proofs anyways. Okay, so we're just going to say on your theorem sheet, I would just make a big category that says chords of circles. And then we'll just number these out. Because there's no reason to try to make up a name for something that we don't need to have a name for. Is that your pink sheet? Thank you. Okay, so number 1 says, in the same circle or congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. In the same circle or congruent circles, 2 minor arcs are congruent if and only if their corresponding chords are congruent. Okay, now this diagram is going to stand out to you guys, I think, because there's not going to be a lot of other diagrams that resemble this. Okay, so I have A, C, and B. And basically what this theorem tells us is that arc AB is congruent to arc BC if and only if segment AB is congruent to segment BC. Okay. Now we do have to remember, what do those words if and only if mean? It's biconditional, so does it only work that way? No, bi. Bi means two. It works 2 ways. Okay, so if they show us that these chords are congruent, we know these arcs are congruent, correct? If they were to show us that these arcs are congruent, then you would know what? The chords are congruent. Okay, so just keep that in mind. That works both directions. If the chords are congruent, the arcs are congruent. If the arcs are congruent, the chords are congruent. Okay. Questions on the first theorem? Okay. Second one. Says that if a diameter of a circle is perpendicular to a chord, then the diameter bisects the chord and its arc. Okay. So, if I have a diameter and it's perpendicular to a chord, messed that up a little bit, but that's a lot better than the diagram in last period. Then it bisects there. And the arc, right? Also bisects the arc. Okay, so if this is true, if I have a diameter that's perpendicular to a chord, then AB, segment AB is congruent to segment BC, and arc AD is congruent to arc DC. Now there has been some confusion that comes on one of our example problems and in the assignment. Does this theorem hold true if my diagram looks like that?
Yes.
Yes. Even though that's not a diameter? It's a radius, which is what? Half of a diameter. Okay, so technically I could, if I wanted to draw it imaginarily, I could extend that to a diameter, right? Okay, I would know it'd be twice as long. So does a radius have the same... My board's all sorts of messed up right now. Does a radius have the same qualities as a diameter does? Yes. What about this? Yes. The theorem still holds true. Now, can it bisect the arc? No, because it doesn't go that far. But if I have a segment coming from the center point and it's perpendicular to a chord, it still bisects the chord. So that segment is still congruent to that segment. Okay? Because could I change this into a diameter? Yes. I could just extend it in both directions and it would be a diameter because it goes through the center point, correct? Okay, so just be aware of that. I got to recalibrate my board. I don't know why all of a sudden today it decides not to work right. Alright, Third one. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Yeah. If one chord is a perpendicular bisector of another chord, then the first chord is a diameter. Basically, it's the converse of number 2. Number 2 said if it's a diameter and it's perpendicular, then it bisects. Here it says if it's a perpendicular bisector, then it's a diameter. So if I have a perpendicular bisector of a chord, then AB is a diameter. Okay. Now, does the first theorem, that is a diagram, look anything like, oh my goodness, either of the second two? No. You should be able to pick out when to use that first theorem. It should be obvious. Okay, your diagram's going to look like this every single time. Okay, so be aware of that. You shouldn't be sitting there wondering, oh, do I use the first one or the second or third? Okay, it should be obvious to us. So, on example 4, not the same example 4 you have in your book, can't do anything because my board's all sorts of messed up. My board's driving me nuts right now. I don't know why it's doing this. It doesn't ever do this. Okay. And I have circle A. I don't know what to do. It hasn't worked good all day, but it hasn't been this bad. I have D, C, B, and they tell me that those two things are congruent. Oh my goodness. Stay calm. Okay. We'll see if we can get through this class period with it. All right. Now, even without having numbers up there, seeing this diagram, you should be able to tell me something. Jacob, what is it? That would be true because of reflexive, yeah, but that doesn't do us a lot of good. But I do agree with you. Vincent? Segments or arcs? Arcs. Because the segments are congruent, I know that these arcs are congruent, correct? Okay, so if I were to put some numbers in here, 3x plus 11 degrees and 2x plus 48 degrees, my fine board writing, and then they asked you to find the measure of arc BC, what would you do? Okay, because if those are congruent, then I can set them equal to each other and solve, right? Okay, so I have 3x plus 11 equals 2x plus 48. Now I just have to start solving it. Subtract 11. Can I also bring the 2x over? Subtract 2x. So here I get x. Here I get nothing. Here I get nothing. Here I get. So my x is 37, but now I have to plug it in. Okay, because now that I know what x equals, I want to find this measure. I plug it in. So I have 2 times 37 plus 48. 2 times 37 is 74. Plus 48 is 122 degrees. Okay. Again, it should have been obvious to use your first theorem on that diagram because of how the diagram looked. One more theorem here. Number 4. If my board will allow it. I don't know what the deal is. Just doesn't feel like doing geometry today, I guess. You guys would say that every day. Alright, last theorem says that in the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center point. In the same circle or congruent circles, two chords are congruent if and only if they are equidistant from the center point. Okay. Now, from our past experience, when I measure a distance to something, what type of angle needs to be formed? A right angle. Okay, I'm not going to measure the distance like this. Okay, that wouldn't make any sense. I'm going to measure the distance at a right angle, correct? Okay, so what they're saying is AB is congruent to CD if and only if EG is congruent to EF. Right? Okay. Now, we have to be aware of these words, if and only if. Again, that's biconditional, correct? So your statement works in both ways. So, with that, if they told me those segments were congruent, or excuse me, those chords, you would also know that they were equidistant to the center, correct? Okay, what else would you know if the chords are congruent? Right, EG and EF would be perpendicular and congruent. You would also know that arc AB is congruent to arc CD. That's not in this theorem, but you still know it, right? Because if the segments are congruent, the arcs have to be congruent. Okay. Last example here. I'm going to recalibrate one more time to see if I can get a good diagram here. This diagram's a little bit confusing. I could do that, but then I don't have it saved. Alright, so I have my circle. And I have segment AB. I have GCE, and I have D. And right here is F. And those are right angles. Before I start doing anything, we got to talk about some things we recognize out here. What do we notice here? What stands out? Jacob? We could, yeah. Eventually we could. Hey, what else? Just things we notice. Doesn't even have to be congruent things. Just things we notice. Angles, shapes. What do we notice up there? Amanda? We have 2 right angles. Hey, that's important because is this a diameter? I mean, almost, but can we think of it as a diameter? So what does it do to this segment? It bisects it, right? Is this a diameter? I mean, it's not, but we can treat it as one, right? Does it bisect? Yes. Hey, what else? Carly? Okay, good. CF and CG are both perpendicular to their chords. What's that? To make them congruent to each other? If these happen to be congruent, then yeah, the segments are going to be congruent. What about shapes? Vincent? CFE is a right triangle. Okay, we can solve right triangles, right? So there's probably some sort of reason why they gave that to us, do you think? Okay, now I'm going to fill in the rest of the things they tell us. They told us that AB is 12 units. They told me that DE is 12 units. And they told me that CE is 7 units. They want to know what is the length of GC. So what were you saying, Carson? CF and CG have to be congruent to each other. Why? Yeah, because our chords are congruent, right? And if my chords are congruent, that means they must be equidistant from the center point, correct? So if somehow I can find that length, do I know this length? Yes. Royal? Why is DF congruent to FE? Because that diameter is doing what? It's perpendicular to a chord, which means that it must bisect it, right? So what is FE? Do I have enough information to find that, Jacob? I can do Pythagorean theorem now with this right triangle, correct? Set that up for us, please, Jacob. Good. So we know 6 squared is 36. 7 squared is 49. Subtract, right? So I get x squared equals 13. What does x equal? Now, technically, it's plus or minus square root of 13, right? But would it make any sense to have a negative square root of 13 as a length? No, because can you have a negative length? No, not possible. So, the length of segment GC is square root of 13. Okay, so just a small example. You might have to use multiple theorems in one problem. Okay, there might be a lot of stuff going on that you have to take care of. So be ready for that. Okay, use those theorems that we talked about to work your way through those problems. Your assignment, remember this is an add-on from yesterday. Right here.